Before we start, I just want to say thanks to everyone who provided feedback on the last video. That was really nice and I really appreciate it. The main takeaway for me was that I should try to speed up my talking a little bit, so we'll give that a try today. How do we model the outcome of an experiment in probability theory? When we discussed the sample space, I told you that the sample space summarizes all outcomes of an experiment. But in this video, I will tell you that random variables are also used to model the outcome of an experiment. So how does this fit together? The difference lies in the fact whether you are looking at the original or a derived experiment. Let me explain that with an example. Let's say you are tossing 3 fair coins and you are interested in the probability to toss 2 heads. We already know that the sample space consists of all possible tuples of length 3, where each element can take the values 0 or 1. But that means that our sigma algebra, which consists of subsets of omega, also consists of subsets of such tuples. Accordingly, our probability measure P can only assign probabilities to subsets of tuples of length 3. But this is not what we are interested in. We are interested in the number of heads that we tossed, which actually is a number between 0 and 3. And for each tuple, we can actually quite easily read off that number. So we need to translate each tuple of omega into the quantity of interest, which in this case is simply the sum of heads tossed. So let's define a function, x, that maps from the probability space to the set of numbers 0 to 3, and for each small omega in the sample space simply computes the sum of the coins represented as zeros and ones. As you can see here, this simple idea effectively solves our problem and transforms the outcome of our original experiment into the outcome of the experiment we are actually interested in. And what I really like about this idea is that it is basically a direct description of what you are doing mentally when you're figuring out how many heads you tossed. Because you look at your coins and count how many heads you tossed. That is, you are actually mapping the result of the original experiment onto the thing you are interested in. Okay, so now that we know how to translate our original experiment into our derived experiment, how do we calculate the probability to toss 2 heads? The problem we have to face is that our probability measure still lives on omega. So we actually need to look for all the outcomes in omega that get mapped onto the number 2 by x. This set, the pre-image of 2, collects all outcomes corresponding to 2 heads, such that the probability of tossing 2 heads is simply the probability assigned to this pre-image. But how do we know that we can actually assign a probability to the set? If you've watched the last video about the necessity of sigma algebras, you know that to be able to assign probabilities here, we actually need to ensure that the pre-image is contained in our sigma algebra on omega, simply because this is the domain of our probability measure. And these two ideas, transforming outcomes with mappings that have measurable pre-images, aren't specific to our coin tossing example. They are actually the core idea behind how random variables are defined in general. Formally, given a probability space omega AP and a measurable space S with sigma algebra calligraphic S, a map X from omega to S with the property that for every measurable set in S, the pre-image under X is a measurable set in omega, is called a random element in S, simply because each realization of X is exactly that, a random element in S. And if S is given by the real numbers, then X is called a random variable. One last comment before we go on to figuring out what distributions are. Did you notice that we imposed that the image space is a measurable space too? Notice that in full generality, This does not impose any restrictions on the choice of our space we are looking at, because we could simply use the power set as sigma algebra. However, basically, as before for measures, this implicitly restricts which random variables we can define, because it limits what can be measurable and what not. This is actually a bit subtle, but through this we create a kind of logical backwards compatibility. If we recall from the previous video that intuitively sigma algebras are the collection of sets about which we can logically reason about, then this means that if we can logically reason about the outcome of a derived experiment, we already need to be able to logically reason about the corresponding original experiment. Okay, so much for this. What is the distribution of a random variable? Basically, we have already seen what's happening. When we calculated the probability for tossing two heads, we looked at the pre-image of the number 2 under x and calculated the probability for this pre-image. And the way you can think about this is that you take the mass on omega that is assigned to this pre-image and push it through x onto the image space. And if we simply do this for all values, all the mass on omega gets distributed over the image space, and since pre-images of disjoint sets are disjoint again, this procedure indeed defines a new probability measure on the image space, which in general is called the push-forward measure, and in probabilistic terms is called the distribution of x. Okay, so let's note that down to our definition. We simply define the distribution of x as the probability measure px on S, and this probability measure should give us, for every measurable set B, the probability that x lies in B. So, as before, the probability that is assigned to the pre-image of B under x. And there you have it. Random variables are measurable functions that describe derived experiments, and their distribution shows how probability mass gets redistributed over the image space. I hope you enjoyed the video and could learn something from it, and thanks for watching.